This is a re-recording of this problem from chapter 16 on the food value, respectively how much heat a burning peanut gives off in order to heat water. It's a re-recording. As you can see, I already worked out the algebra. However, I did make a mistake, and so some numbers that you see here, actually most of them are correct, but my end result is not, and I will erase that once I get there. Okay. Anyway, the problem reads as follows. In lab, Will burns a 0.6 gram peanut beneath 50 grams of water, which increases in temperature from 22 degrees Celsius to 50 degrees Celsius. The amount of heat absorbed by the water can be found with the equation Q equals Cm delta T, where Q is the amount of heat, C the specific heat of water, M the mass of water, and delta T the change in the water's temperature. A. Assuming that 40% of the heat released makes its way to the water, show that the food value of the peanut is 3,500 calories, or 3.5 food calories. That's for capital C. B. What is the food value in calories per gram in food calories, calories, and capital C again per gram. Okay. So, what I have here is 50 grams of water. There's a 0.6 gram peanut that is burning, putting heat into the water, and it says that the amount of heat it puts in is actually only 40% efficient, which means the other 60% are given off to the air or are not reaching the water in other means. That's what's written here, 40% efficiency. These are temperatures of the water, 50 degrees Celsius when it's warm and 22 degrees Celsius when it starts, which means the temperature difference is 28 Celsius degrees. Here's the equation. Heat flow equals the specific heat capacity of water. There it is, 1.00 calories per grams in Celsius degrees. The mass of the water, 50 grams. Notice that the grams here and here divide out, and delta T is 28 degrees Celsius degrees, and again the Celsius degrees divides out, which is the calorie, which means that the calorie survives at the end. So it's 1.00 times 50 times 28, which is 1,400 calories. That so far is the correct result. That's how much heat the water receives. However, then I made a mistake in my first recording, and that is I multiplied with 40%. That is not true. I'll show you what I have to do. 1,400 calories is what the water receives, but that is only 40% of what the burning peanut gives off, which means what the burning peanuts give off must be quite a bit higher. How much higher? Well, what I have to do is not multiply with 40%, but divide by 0.4. Dividing by a percentage is rather strange, so I'm not going to do that, but instead I divide by 0.40. So there it is, divide by 0.40, and then I come up with, and I guess I could make a nicer looking fraction bar. Not fraction bar, but straight line here that gives me my result, and that means after dividing I come up with 3,500 calories. Again, that is the amount of heat that the peanut gives off, 3,500 calories, 40% of which is what the water receives, and 40% of that is the 1,400 calories that I calculated earlier. That one written in food calories are therefore 3.5 calories with a capital C. The second one says part B says what is the food value in calories per gram. So what I'm going to do here is I divide the number of calories, which is now the correct 3,500 calories, divided by 0.6 grams. So, and that comes out to around 5,800 calories per grams, or 5.8 food calories per grams. And now the problem is correct. Okay, number 3, which says pounding a nail into wood makes the nail warmer. Suppose that a hammer exerts an average force of 500 newtons on a 6 centimeter steel nail when it drives into a piece of wood. So we have a force of 500 newtons, that's about 100 pounds, on a 6 centimeter steel nail. So 6 centimeters steel nail. That's a couple of inches. When it drives into a piece of wood, the nail becomes hotter. I know that from trying to screw screws in, and if I don't pre-drill the hole, then wow, yeah, my screw does become pretty warm to the touch, pretty hot. And I noticed that when I try to turn a screwdriver, that it's so hard that I exert a lot of friction, and actually my hands ache and become warm as well. Anyway, if all the heat goes to the nail, calculate its increase in temperature. Assume that the specific heat capacity of steel is 450 joules. So here they're using a different unit. Instead of calories, they use joules. It's the SI unit, the standard unit, 450 joules per kilogram and Celsius degrees. Okay, let's see. The original question was calculate its increase in temperature. So they're asking for by how much does the temperature increase. Well, what I'm doing here is I exert a certain amount of work, and that will be transferred into heat. So I work the nail in there, and then when I'm done, then that energy is gone. Well, it's heat, of course. The work I can define as the force that I exert times the distance, and the heat I can define as the specific heat capacity times the mass times the change in temperature. The first one is going to be 500 newtons times 6 centimeters, so 0.06 meters. Standard units, we're going to come up with 30, and standard units, Newton meters, then will be joules. Nice, because I need that here as well. So here I'm going to have 30 joules, and that equals, because again the work becomes then the heat, and that equals 450 joules per kilogram and Celsius degree times the mass times the temperature difference. Oops, slight problem. We have two unknowns, mass and delta T. I believe in this problem what the author forgot is to supply a mass. So I looked them up, 2-inch nails or 2 1/4-inch nails, and I came up with a mass of 5 grams, or of course 0.005 kilograms. So the delta T here will then calculate as 30 joules, and trying to get a nicer looking fraction bar than what I usually do. 30 joules divided by 450 joules per kilogram Celsius degrees times 0.005 kilograms. These two divide, and I come up with delta T equals 13 Celsius degrees. Notice that divide by the inverse of Celsius degrees, and you're actually multiplying. So 13 Celsius degrees then means that if I start at room temperature of 20 degrees Celsius, I would heat up the nail to 33 degrees Celsius, so from around 70 Fahrenheit to approximately 90 Fahrenheit.